Today, we are exploring a concept that's at the very heart of statistics and data science. How do we update our belief when we get new information? We'll be diving deep into conditional expectation and variance. This isn't just abstract theory, it's the formal way we adjust our forecast and quantify our uncertainty in the face of new data. We'll use simple analogies, a clear example with dice, and a Python verification to make it crystal clear. Before we start conditioning on new information, let's quickly recap the basics. Expectation is simply the long run average of a random variable. It's our best guess of an outcome without any extra information. For a six-sided die, the expectation is 3.5. Variance measures the spread or dispersion around the average. It's a measure of a total uncertainty. For a single die, the variance is about 2.9. With that as the baseline, let's introduce some new information. Conditional expectation is the expected value of a variable given that we know something else. It's our new updated guess. So the best analogy is a weather forecast. The conditional expected rainfall for tomorrow might be half an inch. That's the average for any given day. But the conditional expectation that we know that a category 4 hurricane is just offshore might be 8 inches. The new information radically changes our forecast. Let's use a concrete example, which is the sum of two die. Let y be the sum and let x be the result of the first die only. The unconditional expectation of the sum, which is the expectation on y, is equal to expectation on die 1 plus expectation on die 2, which is equal to 3.5 plus 3.5, which is further equal to 7. But what if I tell you the first die was a 3? What's our new forecast for the sum? This is the conditional expectation, which is the expectation of y given the information that x is equal to 3. Now, the problem becomes much simpler. The sum is now just 3 plus whatever the second die rolls. So the expectation is 3 plus the expectation of the second die, which is 3.5. So the overall expectation is equal to 6.5. The new information, Viricid changed their expectation from 7 to 6.5. This brings us to a beautiful tool that connects our conditional forecast back to the overall average. The law of total expectation. It states that the overall average is just the average of all the conditional averages. Think of it like calculating the average height of all students in a country. You could measure every single student, or you could just find the average height within each school and then take the average of all those school averages. You'll get the same number. So let's quickly verify this with a die example. We calculated that if the first die is a 1, the expected sum is 4.5. And if it's a 2, the expected sum is 5.5, and so on up to 9.5. What's the average of all those conditional expectations? So 4.5 plus 5.5 plus 6.5 plus 7.5 plus 8.5 plus 9.5 divided by 6 is exactly equal to 7. It perfectly matches our original unconditional expectation. Just as our expectation changes, so does our uncertainty. Conditional variance measures the amount of uncertainty that remains after we have received new information. Back to our weather analogy, the unconditional variance for rainfall might be huge because the outcome could be anything from 0 to 10 inches. But the conditional variance, given the hurricane, might be smaller. We are now more certain it will be a high number, maybe between 7 to 9 inches. So the remaining spread is lower. In our die example, we know the result of the first die. The only uncertainty left is the role of the second die. So the conditional variance of the sum is just the variance of a single die, which is about 2.917. Now, let's get to the law of total variance. This is one of the most powerful and insightful formulas in all of statistics. The law of total variance allows us to decompose our total uncertainty into two distinct parts. So, variance of y can be written as expected value of variance of y given x plus variance of expected value of y given x. The first term is the expected amount of the remaining variance. It's the average uncertainty that's left over even after we have our new information. This is the inherent unexplainable randomness in the system. The second term is the variance of the conditional expectations. This is the part of the uncertainty that is explained by our new information. It measures how much a forecast itself becomes, bounces around as we get different information. Think of the student heights again. The total variance in the student heights across the country is the sum of the average variance within the schools plus the variance between the schools' average heights. It's a beautiful way to partition uncertainty. Alright, now let's prove these laws with code. First, I'm creating a simple pandas data frame with all 36 outcomes of rolling 2 die. So this is a sample of the 36 outcomes in our data frame. Now, let's verify the law of total expectation. We'll calculate the overall mean of the sum, and then we'll use the group by to calculate the conditional mean for each possible outcome of the first step. Finally, we'll average all those conditional means. As you can see, the unconditional mean is 7, and the mean of the conditional mean is also 7. They match perfectly, verifying the law of total expectation. Now, let's verify the law of total variance. We then calculate the conditional variance of each outcome of the first die and find their averages. That's our first term. Then we take the conditional means we calculated earlier and find their variance, and that will be our second term. And when we add them together, so the first term we got is 2.9167, and the second term we got is also 2.9167. So when we add them together, we got a sum of 5.8333, which is equal to the total variance, which is also 5.8333. So now we also prove that the law of total variance also holds. Conditional expectation and variance are much more than just textbook formulas. They provide a powerful framework for how we should think about and update our beliefs in the face of new data. Conditional expectation revises our best guess for an outcome, and the conditional variance revises our measure of the uncertainty that remains. The law of total expectation and variance are the tools that allow us to break down complex problems and understand precisely where the uncertainty in our models and forecasts come from.